Hey there, have you ever looked up at the night sky and wondered about those tiny, shimmering points of light? They seem so simple, yet they hold secrets stretching across unimaginable distances and eons of time. Tonight, we're going on a journey to unravel some of those mysteries. We'll explore why some lights twinkle and others hold steady, how our planet's very breath shapes what we see, and the incredible science behind observing the cosmos. It's a story of patience, observation, and the quiet pursuit of understanding. Before we dive in, if you enjoy exploring the wonders of science with us, consider hitting that like button and subscribing. It helps us share these quiet explorations with more curious minds. Now, let's begin our journey back to the very first moments of human wonder. Imagine our ancestors thousands of years ago standing beneath a sky unburdened by city lights. Every night, the same brilliant tapestry would unfold above them. Those shining dots weren't just lights, they were silent, luminous messengers prompting profound questions. What were they? Were they holes in a cosmic blanket, letting through the light of some great fire beyond? Were they gods or the eyes of ancient spirits watching from above? The mystery was immense, and the answers were elusive. Early civilizations across different cultures grappled with these questions. They observed patterns, charted movements, and began to weave stories and philosophies around these celestial bodies. The stars became central to their understanding of the world. Many early cosmological models envisioned the stars as fixed, unmoving points of light, perfect and unchanging. They were often seen as embedded in a series of crystal spheres, rotating around a central Earth, a divine and orderly clockwork. This idea of a celestial sphere with stars as permanent fixtures offered comfort and predictability. It suggested a grand design, a stable universe where everything had its place, guided by unseen forces. The stars were symbols of constancy. Astronomers of antiquity meticulously tracked their paths. They built observatories not with lenses but with carefully aligned stones and sightlines, marking solstices and equinoxes and predicting eclipses based on these perceived fixed points. They gave names to constellations, seeing mythical figures and animals in the star patterns. These celestial maps were not just scientific tools, they were cultural narratives connecting humanity to the vast, silent expanse above. The stars were considered divine or semi-divine, influencing human destiny and earthly events. Their perceived perfection and unchanging nature made them powerful symbols in religion, philosophy, and daily life. For centuries, this view held sway. The stars were simply points of light, eternally fixed, perfect, and perhaps even within reach. The idea of them being anything more was beyond the scope of human understanding at the time. They couldn't know that each pinprick of light was not a hole in the heavens but a distant sun. They couldn't fathom the immense distances or the fiery processes that powered these celestial beacons. Their observations, though limited by the naked eye, were foundational. They represented humanity's earliest attempts to make sense of the cosmos, to impose order on the seemingly chaotic dance of light above. But as centuries turned into millennia, new tools and new ways of thinking began to emerge. The static, perfect stars of ancient philosophy would eventually give way to a more dynamic, awe-inspiring reality. The invention of the telescope marked a pivotal moment. Suddenly, those fixed points of light began to reveal themselves as something far grander, far more complex, and infinitely more distant than ever imagined. Modern science unveiled a breathtaking truth. Stars are not tiny holes or perfect gems on a sphere. They are immense fusion reactors, colossal balls of gas burning brightly across unimaginable cosmic distances. Deep within their cores, atoms are crushed together under immense pressure and heat, releasing vast amounts of energy in a process called nuclear fusion. This energy bursts forth as light, traveling outwards in every direction. That light, the very thing we see when we look up, has journeyed for years, decades, even centuries across the cold, vast emptiness of space. It's a testament to the sheer power and scale of the universe. Each photon, a tiny packet of light, is a messenger carrying information from the star's fiery heart. It travels uninterrupted for light years, crossing interstellar voids until it finally reaches our planet. And it's at that point, just as it's about to reach our eyes, that something truly fascinating happens. This ancient light, having crossed the cosmos, encounters Earth's atmosphere. Our atmosphere, a thin, dynamic blanket of air, becomes a silent, invisible filter. It's here that the story of stellar scintillation, the twinkling of stars, truly begins to unfold. This journey of light from the heart of a star to our eyes is a narrative filled with unexpected twists. It's a tale of physics, observation, and the subtle dance between light and matter. In the coming chapters, we'll delve into the precise ways our atmosphere plays tricks on starlight, distinguishing stars from planets, and revealing the hidden stories these luminous messengers carry. For now, simply appreciate that every twinkling star is a distant sun, its light having traveled an immense journey, carrying a tale as old as time itself. The true mystery is just beginning. The ancient view of static, perfect stars had begun to yield. Yet, to truly understand those luminous messengers, humanity first needed to grasp the very nature of light itself. What was this elusive phenomenon that traveled from distant suns to our eyes? In the quiet solitude of his chambers, a scientist of the 17th century, Isaac Newton, began to question the prevailing ideas. He observed light not just as a source of illumination, but as a phenomenon to be dissected, understood. His experiments were simple yet profound. He directed a beam of sunlight through a glass prism. What emerged on the other side was not just white light, but a vibrant spectrum of colors: red, orange, yellow, green, blue, indigo, violet. This was a revelation. It suggested that white light, seemingly uniform, was in fact a composite. It held within it all the colors of the rainbow, each bent at a slightly different angle by the prism. Newton's work, meticulously documented, hinted at light's complex nature. It was not merely a thing that illuminated, but a phenomenon with intrinsic properties, a hidden internal structure waiting to be unveiled. Around the same time, others pondered light's fundamental form. Was it a stream of tiny particles like miniature bullets? Or was it a wave rippling through an unseen medium, much like sound through air or ripples on a pond? The idea of light traveling at a finite speed was another conceptual leap. For centuries, it was assumed light was instantaneous, appearing everywhere at once. How could one measure something so incredibly fast? Early attempts to measure its speed were ingenious. Ole Romer, observing the eclipses of Jupiter's moons, noticed slight variations in their timing depending on Earth's position in its orbit. This suggested light took time to cross the varying distances. These small discrepancies, though challenging to measure precisely, provided the first solid evidence that light did not travel infinitely fast. It had a measurable, albeit immense, velocity. Later, in the 19th century, scientists like Fizeau and Michelson devised clever terrestrial experiments using rapidly rotating mirrors. They sent light over long distances, bouncing it back, and measured the tiny time difference. These precise measurements confirmed light's incredible speed, approximately 299, 792, 458 meters per second in a vacuum. A number so vast it's almost beyond comprehension. This understanding of light's finite speed had profound implications for astronomy. If light took time to travel, then the light reaching us from distant stars was not live. It was a glimpse into the past. To describe these immense cosmic distances, a new unit was born, the light year. It was not a measure of time, but a measure of distance, the distance light travels in one Earth year. Suddenly, the seemingly fixed stars gained an incredible depth. Alpha Centauri, our closest stellar neighbor, is about 3 light-years away. This means the light we see from it tonight began its journey over 4 years ago. For stars in distant galaxies, the numbers stretch into millions or even billions of light-years. The light from some of these celestial beacons began its voyage before Earth even existed. This new perspective transformed the cosmos. Each twinkling point of light became a time capsule, carrying ancient photons that had traveled unimaginable distances across vast cosmic voids. Consider a single photon, born in the fiery heart of a star. It embarks on a journey. It escapes the star's surface, then navigates the emptiness of interstellar space, undisturbed for millennia. Its path is straight, unwavering, until it approaches our solar system. It zips past planets and moons, a silent, ancient messenger carrying information about its distant origin. Then, just as it nears Earth, its long, quiet journey is abruptly interrupted. This ancient photon, having traveled billions of miles, encounters our planet's atmosphere. Our atmosphere, a relatively thin shell of gases, is a dynamic, ever-changing medium. It's a swirling ocean of air, currents, and temperature variations. This encounter is crucial. It's where the story of why stars twinkle and planets don't truly begins to unfold. The journey of light is not over once it reaches Earth's vicinity. The atmosphere acts as a subtle, invisible lens, constantly shifting and distorting the incoming starlight. It's a dance between ancient light and turbulent air. Scientists, through careful observation and ingenious experiments, began to connect these atmospheric disturbances to the shimmering appearance of stars. The very air we breathe, the air that sustains life, also subtly alters our view of the cosmos. It adds another layer of mystery, another puzzle to solve in the grand narrative of light. In the next chapter, we will delve deeper into this atmospheric dance, understanding how this thin veil of air transforms steady beams of starlight into those familiar, captivating twinkles. The journey continues. The long journey of starlight, spanning cosmic voids, culminates as it approaches our home. But here, just before reaching our eyes, it encounters something profound: Earth's atmosphere. This isn't empty space, but a tangible, dynamic ocean of air. For centuries, the air above us was often taken for granted, an invisible medium. Yet, early observers, with their keen eyes and simple instruments, began to sense its presence, its subtle influence on the celestial tapestry. Unlike the near-perfect vacuum of interstellar space, Earth's atmosphere is a thick, swirling envelope. It is a mixture of gases, dust, and water vapor, constantly in motion, sculpted by temperature and pressure. The emerging science of meteorology in the 18th and 19th centuries began to map this invisible ocean. Scientists charted wind patterns, temperature gradients, and the rise and fall of atmospheric pressure. Imagine looking at a distant object across a large body of water. On a calm day, the view is clear, but if the water is agitated, rippling, and churning, the object seems to waver, its edges blurring and shifting. This gentle analogy helps us understand what happens to starlight. The light, having traveled undisturbed for eons, suddenly encounters an environment that is anything but still. It's like looking through agitated, rippling water. Each tiny parcel of air, with its unique temperature and density, acts like a minuscule lens, subtly bending the incoming starlight. As these parcels of air move, the bending effect constantly changes. This constant minute distortion causes the starlight to shimmer, to appear to twinkle. It's not the star itself changing, but our view of it being disturbed by the restless air above us. Early astronomers, though without the full understanding of atmospheric physics, began to sense this. They observed that stars low on the horizon twinkled more violently than those directly overhead. This simple observation was a crucial clue. It suggested that the twinkle was not intrinsic to the star, but rather a phenomenon connected to the amount of Earth's atmosphere the starlight had to traverse. The intuition grew. Perhaps the shimmering wasn't from the distant celestial body, but from something closer to home. The very air we breathed, the air that seemed so transparent, was the culprit. Scientists began to turn their attention not just to the stars, but to the invisible ocean of air surrounding our planet. They sought to understand its layers, its currents, and its ever-changing nature. The atmosphere is not uniform. It consists of layers, each with different temperatures and densities. Warm air rises, cool air sinks, creating constant convection currents. These invisible currents, like eddies in a vast ocean, are continually shifting the air's density and refractive index, its ability to bend light. This creates pockets of slightly different optical properties. As starlight plunges through this dynamic veil, it passes through countless such pockets. Each one subtly deflects the light, causing it to arrive at our eyes from a slightly different angle, a fraction of a second later. This phenomenon, known as atmospheric refraction, is responsible for the slight bending of light that makes stars appear higher in the sky than they actually are, especially near the horizon. But it's the changing nature of this refraction, the constant movement of the air, that creates the visible effect of twinkling. The air is never truly still. Even the heat rising from the ground or the subtle flow of air currents contributes to this atmospheric dance. Every breath of wind, every temperature fluctuation adds to the shimmering effect. This understanding transformed the atmosphere from a mere void to a crucial component of astronomical observation. It was a shifting canvas, painted by the unseen forces of Earth's own environment. The development of weather balloons and instruments to measure atmospheric conditions at different altitudes further solidified this understanding. The veil was being lifted, layer by layer. Researchers meticulously mapped the atmosphere's properties, correlating them with observations of stellar twinkling. The evidence was compelling. The twinkle was truly an earthly phenomenon. Yet a new question arose from this understanding. If the atmosphere made stars twinkle, why did some bright points of light in the night sky remain steadfast, unblinking? This subtle difference between the twinkling stars and the steady lights held another key to unlocking the secrets of the cosmos. It was a distinction that would help us truly differentiate between distant suns and closer worlds. The atmosphere, this dynamic, living ocean of air, was not just a filter. It was an active participant in our cosmic observations, sometimes obscuring, sometimes revealing. In the next chapter, we will explore this crucial distinction, understanding why some celestial bodies pierce Earth's veil with unwavering light, while others dance and shimmer. The mystery continues to unfold. The long journey of starlight, spanning cosmic voids, culminates as it approaches our home. But here, just before reaching our eyes, it encounters something profound: Earth's atmosphere. This isn't empty space, but a tangible, dynamic ocean of air. We've learned that this veil of air is a shifting canvas. But what exactly in this air causes the light to waver? The answer lies in its subtle, invisible variations. Air, seemingly uniform, is actually a patchwork. It's filled with countless pockets, each with slightly different temperatures and densities, constantly forming and dissolving. Think of warm air rising and cool air sinking, a constant, invisible convection. This creates a churning, turbulent environment, like countless tiny, swirling eddies within a vast ocean. These eddies are the air pockets we speak of. Each one is a fleeting, distinct parcel of air, unique in its temperature and density, even if only by a fraction. Crucially, the density of air directly affects its refractive index, its ability to bend light. A warmer, less dense pocket will bend light differently than a cooler, denser one. You've likely seen this effect: the shimmering air above a hot road on a summer day, or the wavering distortions above a campfire. That's the principle at play, but on a grander, atmospheric scale. Now, imagine starlight, having traveled billions of miles in a perfectly straight line, suddenly plunging into this restless, turbulent ocean of air. Each of these tiny, shifting air pockets acts like a miniature, imperfect lens. They are not static but transient, constantly forming and dissipating. As the starlight passes through one of these invisible lenses, it is subtly bent or refracted, ever so slightly, in a new direction. Because the air pockets are in constant motion, the light from a distant star is continuously being bent, unbent, and rebent along its path to our eyes. This means that the light from a single point-like star arrives at our eye not as a steady, focused beam, but as a rapid succession of slightly displaced rays. The star's apparent position in the sky seems to dance, flickering rapidly from one tiny point to another, hundreds of times per second. Simultaneously, the amount of light reaching our eye also fluctuates, causing the star to appear momentarily brighter, then dimmer, then brighter again. These rapid, continuous changes in both position and brightness are what we perceive as the familiar twinkling or stellar scintillation. For early telescopic astronomers, this atmospheric interference was a constant source of frustration. It blurred their views and made precise measurements difficult. They quickly realized that the clarity of their observations depended not just on the telescope itself, but on the steadiness of the air above them. This led to the formal concept of atmospheric seeing, an astronomer's term for how stable or turbulent the air is, and how clearly celestial objects can be observed. On nights of good seeing, the air is relatively calm, allowing starlight to pass through with minimal distortion, resulting in crisp, steady images. Conversely, poor seeing nights are marked by highly turbulent air, leading to intensely shimmering, blurry views, making fine details impossible to discern. This understanding profoundly influenced where observatories were built. High, dry mountain peaks, far from city lights and ground-level turbulence, became preferred sites. Scientists developed ingenious instruments and techniques to measure and characterize atmospheric seeing, striving to predict the best nights for observation. Even with today's advanced adaptive optics, which actively correct for atmospheric distortion, seeing remains a fundamental limit to ground-based astronomical observation. The dance of air pockets, this invisible ballet of turbulence, is a constant, subtle force shaping our perception of the cosmos, adding a layer of mystery to every star. But this intricate atmospheric dance, while affecting all incoming light, impacts different celestial objects in distinct ways. This crucial difference holds another key to unlocking the secrets of the night sky. We have explored the turbulent dance of air pockets, this invisible ballet within Earth's atmosphere. These tiny, shifting lenses are the key to understanding why starlight behaves as it does upon reaching our planet. For centuries, the shimmering of stars was simply a beautiful mystery. But with the advent of scientific inquiry into atmospheric optics, a direct link began to emerge. The turbulence was not just an annoyance, it was the cause. Researchers in the mid-20th century, armed with new instruments and a deeper understanding of fluid dynamics, began to quantify this effect. They sought to map the precise ways light was altered. The crucial insight lay in understanding the nature of a star as a source of light. Unlike a planet which appears as a small disk, a star is so incredibly distant it acts as an infinitesimal point source. Imagine light leaving a star. Over light years of travel, the individual rays from that star become virtually parallel by the time they reach Earth. They are like an infinitely narrow, perfectly straight beam. This parallel beam, originating from a single distant point, is fundamental. It means all the light we receive from one star is, in essence, coming from the very same direction. This point source characteristic is what makes stars twinkle and planets typically do not. It's a subtle but profound difference in how their light interacts with our atmosphere. As this perfectly parallel starlight plunges into Earth's turbulent atmospheric layers, it encounters those constantly shifting air pockets we discussed. Each pocket has a slightly different refractive index. Each tiny parcel of air acts like a miniature, imperfect lens, and because these parcels are in constant motion, the path of the starlight is continuously, wildly altered. The light rays from that single distant point source, once parallel, are now sent along wildly varying paths. They are bent, straightened, and bent again, all within moments. Think of it as looking at a distant light through a pane of glass that is constantly rippling and warping. The light itself is steady, but the medium through which you view it is not. The scientific challenge was to model these complex light paths. How could seemingly random atmospheric movements produce such a consistent visual effect? The key was understanding that the air pockets cause the light rays to converge and diverge. At any given instant, some of these bent rays might cross paths and reinforce each other. When the rays converge, more light from the star reaches our eye at that precise moment. This causes the star to appear momentarily brighter. Conversely, when the rays diverge, they spread out and fewer photons reach our eye. This makes the star appear to dim, sometimes almost vanishing for an instant. This rapid succession of converging and diverging light creates the flickering effect, the brightening and dimming that is so characteristic of stellar twinkling. But it's not just the brightness that changes. The constant bending and rebending of light also causes the star's apparent position to subtly shift. Because the atmosphere is a turbulent, moving medium, the point where the light finally converges on our retina is never truly static. It's constantly being nudged. These minute-rapid shifts in apparent position, combined with the brightness fluctuations, create the complete effect of scintillation. The star seems to dance in the sky. The mid-20th century saw dedicated studies of this phenomenon, quantifying the degree of scintillation under various atmospheric conditions. It was a rigorous pursuit of understanding. These studies confirmed the direct scientific link. Atmospheric turbulence causes light rays from a single distant point source, a star, to follow wildly varying paths. This understanding solidified the role of Earth's atmosphere as an active participant in our astronomical observations, not just a passive filter. It explained why observatories sought high, dry locations where the air is thinner and less turbulent, minimizing the scintillation that blurs telescopic views. The twinkle, then, is not a property of the star itself, but an atmospheric signature. It's the story of ancient light having crossed vast cosmic distances, encountering the restless air of our own world. But if all stars are point sources, why do some celestial lights remain steadfast, piercing the veil of air without a flicker? This subtle difference holds another secret, one that helps us truly distinguish between the distant suns and our closer neighbors. We have seen how Earth's turbulent atmosphere makes distant stars shimmer and dance. Yet, some of the brightest lights in the night sky remain steadfast, piercing the veil of air without a flicker. This subtle difference holds a profound secret about the cosmos. For centuries before the advent of the telescope, both stars and these steady lights appeared as mere points to the naked eye. Their unwavering nature was simply noted, often with a sense of wonder, but without a clear explanation for the distinction. Then came the early 17th century, and with it, a revolutionary instrument, the telescope. Suddenly, the heavens were no longer just a scattering of points. New details began to emerge, challenging ancient beliefs. Galileo Galilei, with his improved spyglass, turned it skyward. He meticulously documented what he saw, pushing the boundaries of human perception. His observations would forever change our understanding of the universe. What Galileo discovered was astonishing. While distant stars remained pinpricks of light, even through his telescope, certain bright stars resolved into tiny, discernible disks. These were the planets, our closer celestial neighbors. This was the fundamental distinction. Stars are so incredibly far away that their light reaches us as if from an infinitesimal point. Planets, by contrast, are much closer and therefore present a measurable angular size. To understand this, imagine a distant light bulb filament. Even with powerful binoculars, it remains a mere point of light, its true shape indistinguishable due to immense distance. Now imagine a distant, luminous billboard. While still far away, it presents a larger surface. With binoculars, you might just discern its rectangular shape, even if the fine print remains unreadable. This analogy helps. A star is like that distant light bulb filament, a true point source. A planet, however, is like that distant billboard, an extended source, however small it may appear. When the perfectly parallel light rays from a distant, point-like star encounter Earth's turbulent atmosphere, the entire narrow beam is affected. All the light is bent and shifted together. But for a planet, light originates from many points across its visible disk. Each of these tiny mini-points on the planet's surface sends its own set of light rays towards Earth. As the light from a planet's disk enters the atmosphere, different parts of its broad light cone encounter different air pockets. Each segment of the incoming light is independently distorted. Consider the light from the left edge of a planet's disk being momentarily bent away from our eye. At the very same instant, light from the right edge or the center might be bent into our eye. Because the planet presents a discernible disk, our eye receives light rays from numerous points across its surface simultaneously. It's a collection of light, not a single, fragile beam. Even if individual rays from the planet are momentarily deflected, the sheer number of light rays arriving from its extended surface means that enough light always reaches our eye. The atmospheric distortions, while still present, are effectively averaged out across the planet's larger apparent size. The eye perceives a continuous, steady glow. This averaging effect is why planets don't twinkle. Their extended disk acts as a buffer against the atmospheric turbulence, ensuring a consistent flow of light to our perception. Galileo's simple act of observation, differentiating the disk of a planet from the point of a star, was a monumental step. It wasn't just about seeing, it was about understanding scale and proximity. This distinction allowed astronomers to truly separate the objects within our own solar system from the vast, distant suns beyond. It reinforced Earth's place not at the center but as part of a larger, moving system. The steady light of a planet became a silent testament to its relative closeness, a marker that allowed early astronomers to track their orbits with greater precision, unhindered by atmospheric shimmer. This understanding of why planets don't twinkle became a fundamental piece of astronomical knowledge, a simple yet profound lesson in how our atmosphere mediates our view of the cosmos. It revealed that the seeing conditions, the turbulence of the air, affected stars and planets differently due to their apparent size, not their intrinsic nature. This knowledge was crucial for future observations, helping astronomers differentiate between an atmospheric effect and a true celestial phenomenon, paving the way for more accurate measurements of planetary motions. The steady glow of planets reminds us that not all celestial lights are created equal, and that our atmosphere, while a filter, also provides clues to the true nature and distance of the objects we observe. Yet, even with this newfound clarity, the universe held countless more secrets. What other stories did starlight carry beyond its twinkling dance or steady glow? The journey into the secrets of the sky had only just begun. Even with the clarity gained from distinguishing stars from planets, the turbulent veil of Earth's atmosphere remained a fundamental impediment. It blurred the finest details, obscuring the universe's most subtle features. For ground-based astronomers, the restless air was a constant battle. Nights of good seeing were rare gifts, allowing fleeting moments of clarity before the shimmering returned. Observation revealed a pattern. The higher the elevation, the less the air distorted light. Thinner air, less turbulence, a simple yet profound insight. This understanding led to a new era of astronomical site selection. Instead of building near cities, telescopes began to ascend, seeking the serene quiet of mountain peaks. High mountains, especially those in arid regions, offered a thinner, more stable atmosphere. Less water vapor and fewer thermal currents meant clearer, steadier views. Constructing vast observatories on remote, windswept summits was a monumental undertaking, demanding incredible engineering and unwavering dedication. Sites like Mount Wilson in California and later Mauna Kea in Hawaii became beacons of this new approach, pushing the boundaries of what could be seen from Earth. Yet even the best mountain sites could not entirely escape Earth's atmospheric embrace. The twinkle, though lessened, persisted, a fundamental limit to resolution. The pursuit of ever-sharper images fueled a new kind of ingenuity. If the atmosphere couldn't be avoided, could it be actively counteracted? The idea emerged: what if we could measure the atmospheric distortion in real time and then precisely reverse its effect before the light reached our instruments? This revolutionary concept birthed adaptive optics. It was a bold leap, transforming passive observation into active, dynamic correction. At its heart lay the deformable mirror, a precisely engineered surface that could change its shape thousands of times per second, guided by sophisticated sensors. Light from a bright reference star was analyzed by a wavefront sensor, instantly mapping the atmospheric distortions. This map then instructed the deformable mirror. When a natural bright star wasn't available nearby, powerful lasers were used to create an artificial guide star high in the atmosphere, a brilliant beacon for correction. The system worked in a rapid feedback loop. Measure, deform, measure again. This constant, lightning-fast adjustment untwinkled the star. The results were breathtaking. What was once a shimmering blur transformed into a crisp, steady image, revealing details previously obscured by our own air. Adaptive optics allowed ground-based telescopes to achieve near space-like resolution, but it was a battle against the elements, a constant technological struggle. The ultimate solution, however, lay in a truly audacious idea: escape Earth's atmosphere entirely. Place a telescope where the air could never interfere. This vision led to the concept of space telescopes, orbiting high above the atmospheric veil, offering an unblinking eye on the cosmos. The dream materialized with the launch of the Hubble Space Telescope in 1990, a testament to decades of scientific and engineering perseverance. From its perch, Hubble delivered images of unprecedented clarity and depth, unveiling galaxies, nebulae, and stellar nurseries with astonishing detail, free from atmospheric blur. Yet space telescopes presented their own challenges. immense cost, complex deployment, and the difficulty of repair in the harsh vacuum of space. The journey continued with the James Webb Space Telescope, designed to peer even further back in time into the universe's infancy. JWST, operating in infrared light, allowed scientists to pierce through cosmic dust clouds and observe the very first galaxies forming, unseen by previous instruments. These twin approaches, taming the twinkle from the ground and escaping it from above, have profoundly deepened our cosmic understanding. But what stories do these clearer views reveal? The relentless pursuit of clearer views, whether by taming the twinkle from the ground or escaping Earth's veil from space, profoundly transformed our understanding. Suddenly, the universe, once a shimmering enigma, began to reveal its true, intricate details. This newfound clarity was not merely an aesthetic improvement. It allowed astronomers to resolve celestial objects with unprecedented precision, distinguishing structures and features previously blurred beyond recognition. Adaptive optics on ground-based telescopes, by actively canceling out atmospheric distortions, brought distant stars into crisp focus. Simultaneously, space telescopes orbiting above the turbulence offered an unblinking, pristine gaze. With the twinkle tamed, measurements became far more accurate. The precise positions of stars, their subtle movements, and their true brightness could be determined with a level of fidelity previously unimaginable. Pinpointing a star's exact location, free from atmospheric jitter, allowed scientists to track its proper motion, its actual movement across the sky with exquisite detail, revealing the dynamic nature of our galaxy. Faint companions to bright stars, once lost in the atmospheric blur, now emerged. Binary star systems, so close they appeared as one, could finally be resolved into their individual components, revealing their orbital dance. The ability to gather light more efficiently without constant atmospheric scattering also meant fainter objects could be detected. Whispers of light from the universe's most distant reaches became audible. Each clearer image, each precise measurement was like deciphering a new sentence in the cosmic story. The subtle variations in starlight, once obscured, now carried profound information about their origins and evolution. One of the most profound impacts of this enhanced clarity was the revolution in exoplanet discovery. Finding distant worlds orbiting other stars required detecting incredibly subtle changes in starlight. When a planet passes in front of its host star, it causes a minuscule dip in the star's brightness. Without atmospheric noise, these tiny, fleeting dimmings could be reliably detected and measured. The precision gained allowed scientists not only to find exoplanets but to begin characterizing them. The depth of the light curve revealed the planet's size, its periodicity, the orbital period. Even more challenging was the direct imaging of exoplanets. This required blocking out the overwhelming glare of the host star to see the faint, reflected light of its orbiting world. Adaptive optics, by creating a super-sharp image of the star, allowed instruments to precisely block its light, revealing the tiny speck of an exoplanet hiding in its immediate vicinity. Each new exoplanet discovery reshaped our understanding of planetary formation and the sheer diversity of worlds beyond our solar system. The universe teemed with possibilities. The impact extended far beyond our galactic neighborhood. Distant galaxies, once fuzzy smudges, transformed into intricate spirals, elliptical giants, and irregular wisps, revealing their hidden structures. In some nearby galaxies, the resolution became so fine that individual stars, once indistinguishable, could be resolved. This allowed for precise measurements of cosmic distances. By observing galaxies at different distances and thus different points in cosmic time, astronomers could reconstruct their evolutionary pathways, understanding how these vast islands of stars formed and changed. The ability to pierce through atmospheric haze and cosmic dust allowed instruments like the James Webb Space Telescope to peer back to the universe's infancy, observing the very first galaxies forming. These ancient lights, having traveled for billions of years, carried the stories of the early cosmos. They revealed how light elements forged in the Big Bang coalesced into the first stars and galaxies. Paradoxically, the very atmosphere that once vexed astronomers became a fascinating subject of study in its own right. Understanding its turbulence was key to overcoming it. Scientists developed sophisticated atmospheric models predicting seeing conditions with greater accuracy. This aided not only astronomy but also weather forecasting and climate science. The detailed study of atmospheric layers, their temperatures, and their movements revealed complexities that aided both ground-based observation techniques and our general understanding of Earth's dynamic environment. This symbiotic relationship, where the quest for cosmic clarity led to deeper insights into our own planet's atmosphere, highlighted the interconnectedness of scientific disciplines. The journey to overcome the twinkle continues. New generations of adaptive optics systems, larger space telescopes, and innovative ground-based techniques are constantly pushing the boundaries of what we can see and measure. Each clearer view from beyond the twinkle deepens our appreciation for the cosmos and our place within it. But what do these precise measurements and stunning images truly tell us about the hidden stories of starlight itself? That we will explore next. We began our journey deep within a star where unimaginable pressures forge light from the heart of fusion. Each photon born there, a tiny packet of energy, embarked on a journey of pure, unblemished light. It traveled for years, decades, even millennia across the silent, cold expanse of interstellar space. Billions of miles dissolved behind it, a testament to the sheer scale of the cosmos and the speed of light. Then, as if drawn by an unseen force, this ancient light approached our small, vibrant world. Its long, quiet voyage was nearly complete, but a final, profound encounter awaited it. It plunged into Earth's atmosphere, a dynamic, ever-changing ocean of air. No longer in the serene vacuum, the light now interacted with countless pockets of varying temperature and density. These invisible eddies and currents, like countless tiny lenses, subtly bent and redirected the starlight. This was the atmospheric dance, the subtle interaction that shaped what we ultimately perceived. Finally, after its epic journey across the universe and through our planet's veil, the light reached our eyes. The journey from cosmic furnace to human perception was complete. For centuries, the twinkling of stars was simply a beautiful mystery, sometimes seen as a flaw that obscured the heavens. But through careful observation and scientific inquiry, its true nature emerged. We learned that stellar scintillation is not a defect, but an intimate signature. It is Earth's own unique, gentle touch upon the ancient light from afar. Consider the poetic beauty in this interaction. The very air we breathe, the atmosphere that nurtures life, also adds a unique shimmer to the cosmos we observe. It is our planet's atmospheric fingerprint, imprinted on every distant sunbeam, a reminder that our perspective, our very place in the universe, is unique. The atmosphere acts as a living lens, constantly shifting, subtly altering the light. This makes our view of the night sky distinct from any other vantage point in the solar system. It's a beautiful dance between ancient light and turbulent air, a constant, subtle reminder of the dynamic forces that shape our world and our perception. Even as we developed technologies like adaptive optics to untwinkle the stars, that natural shimmer remains a fundamental aspect of Earth-based observation. The twinkle is not a sign of imperfection, but of the universe's interaction with our home. It's a natural phenomenon woven into the fabric of our cosmic experience. It reminds us that even with the most advanced instruments, our view of the cosmos is always mediated by our planet, its atmosphere acting as a gentle, ever-present filter. Every twinkling star, every steady planet, every whisper of light from beyond carries a story. These are narratives of creation, evolution, and the boundless mystery of existence. Each photon that reaches us is a timeless messenger, having traveled billions of years to deliver its tale. It tells us about the universe's past, from the birth of galaxies to the death of stars. The light from distant supernovae recounts the violent ends of massive stars, scattering the heavy elements that form planets and, eventually, life itself. The ancient light from the first galaxies, captured by instruments like the James Webb Space Telescope, allows us to glimpse the universe's infancy, its very first moments of illumination. These narratives, carried by starlight, inspire our present quest for knowledge. They drive us to build larger telescopes, develop new technologies, and push the boundaries of what is known. The pursuit of understanding the cosmos is a testament to human curiosity, a relentless desire to unravel the universe's grand design and our place within it. This ongoing quest guides our future exploration. Every discovery, every answered question opens doors to countless new mysteries, beckoning us further into the cosmic unknown. The twinkling of a star, once a simple observation, has led us on a profound journey, from the heart of a distant sun, through the vastness of space, and into the very fabric of our atmosphere. It is a story of light, air, and perception, revealing how intimately connected we are to the universe and how much beauty lies in understanding its subtle complexities. And so, as the moon climbs high and the stars continue their ancient, silent dance, we are left with a profound sense of wonder. The universe, in all its intricate beauty, continues to call to us, "Sleep well."